We are Wisconsin Robotics, and we are proud to present our 2023 URC Rover Eclipse. This year, we increased functionality while maintaining our previous system's reliability.
This year's drive system consists of a returning six-wheel rocker bogie designed with a vertical differential bar.
The rocker bogie system acts as an active suspension, allowing for even distribution of rover loads and impacts over bumpy surfaces and rough terrain. Each wheel consists of aluminum spokes surrounded by a Kevlar shell with ingrained grousers that will allow for proper traction in the sandy competition environment. This season, each wheel has been redesigned with an upgraded assembly. Each wheel is now driven by a powerful brushless motor connected to a planetary gearbox that will allow for increased speed, torque, and efficiency of the drive system compared to previous years. This robust design will ensure lasting durability throughout the competition, challenges, and seasons ahead.
The arm provides a strong, dynamic, and robust system for grasping and manipulation.
It has a 6 degree of freedom kinematically redundant design made to maximize joint efficiency while keeping the weight to a minimum. The arm is more than capable of reaching the 1.5 meter height range and carrying 5 kilograms of weight. Encoders are placed on each joint to allow the use of inverse kinematic control. The end effector uses a high torque NZR back drive system. The claws of the end effector can grasp more than the 5 centimeter requirement, and the tips of the claws are flexible, allowing them to conform to the object's shape.
This year, Wisconsin Robotics has decided to incorporate a drone with the Rover for the autonomous mission.
We control our drone with a Pixhawk flight controller and an NVIDIA Jetson Nano. The Pixhawk is a reliable flight controller that we will use when we manually control the drone, and the Jetson Nano is used as our main processor for autonomous missions. The drone will have several cameras that will help in detecting the Aruco post during an autonomous navigation mission. We use a stereo camera system in conjunction with computer vision techniques such as template matching algorithms found in the Aruco library. In addition to the cameras on our drone, we will be using sensors like GPS, optical flow, and LiDAR to improve the accuracy and reliability of our detection system. Furthermore, the team is using Gazebo, a simulation environment that allows us to safely test our drone to make sure that our code works properly before taking it outside for outdoor testing.
The Science Box collects, stores, and analyzes soil samples for biosignatures and indicators of habitability. In order to run our onboard soil tests, a scoop collects soil from test sites and deposits it into a funnel. Once the soil is deposited, the funnel splits the soil into 5 colorimetric tests on board the Science Box, which test the sample pH and look for ammonia, proteins, nitrogen, phosphorus, and potassium. The modular turntable can also hold sample containers for further analysis of biologically significant samples. A Raman spectrometer sits next to the turntable. Looking at the soil sample's Raman spectra allows us to determine what types of molecules are in the soil, making the Raman spectrometer a powerful tool. Finally, we have a USB microscope and a moisture sensor, which are lowered to the ground by a linear actuator.
The Wisconsin Robotics software team is focused on delivering reliable and robust software for all subsystems of the rover.
The arm now features an inverse kinematics control scheme, which gives the drivers more reliable and intuitive control of the arm. The arm control software also features control loop-based driving to hold the position of the arm and safety stops to prevent damage to the rover arm or grasped objects. The software has also been upgraded to support the new drive motors and take advantage of the advanced features in the new motor controllers. Additionally, the software team migrated our code to the Raspberry Pi to efficiently communicate with the new hardware and utilize the GPIO capabilities of the Pi. We are also testing the autonomous navigation software and integrating our current driving algorithms with the drone for the autonomous navigation mission.
The chassis team has made several improvements to the rover's electrical system, including a new enclosure, adding robust GPIO capabilities, and upgrading the power distribution board.
First, we have designed a new enclosure. This enclosure will have interchangeable layers so that we can have ease of access to each of the layers. Next, we have switched our main onboard computer to a Raspberry Pi. This will allow us to integrate many of our new sensors, such as a time of flight sensor and an RP LiDAR module for autonomous navigation. A new distribution board has also been integrated into the rover system. This board houses the IMU and GPS and is the interface between the Pi and all onboard actuators, allowing us for improved actuation and intelligence of our rover.
The team leverages several testing platforms to ensure competition readiness for Eclipse. To test the dexterity of our arm, our team uses a test box that contains many of the equipment servicing and ERDM challenges, such as switches, USB ports, and a keyboard. We use a 5 kilogram toolbox with a handle to ensure the arm has sufficient carrying strength for competition. The team tests full system functionality on the snowy hills and fields of UW-Madison, focusing on long-distance communications, teleoperation practice, and multiple drive environments. With our system design and preparation for competition, Wisconsin Robotics is ready to tackle the 2023 University Rover Challenge.